It is a pleasure for me to welcome you to my talk about the technology highlights in our new release Geodict 2023 at this year's Geodict user meeting. But first, something about myself. My name is Eric Klatt and I am the Chief Technology Officer of Master Market, the company behind the software Geodict. In this role, I oversee scientific and technological aspects of product planning and development. Before my time at Master Market, I worked at the Fraunhofer ITWM as a researcher. I hold a PhD in theoretical physics from the Technical University in Darmstadt. Before I start with the technology highlights, I want to point out that the Geodict 2023 release is out now. We recommend to download and test it, as we think the new Geodict release is the best solution for digital material analysis and design. With the new release, you can explore all the new features I'm going to present in the following slides. What we mean with digital material analysis and design mentioned on the slide before is shown in the workflow on the current slide. It often starts with the input of a 3D image of a real material. Afterwards, the image is analyzed to understand the material and its properties. This step alone can already be very useful. If one understands the material's geometric properties, one can create a statistical digital twin. Having this twin, one can start to design or engineer a next-generation material with improved properties. In this way, Geodict can help to design improved materials faster and cheaper. This workflow will aid me now as guideline to walk you through the technology highlights in Geodict 2023. In this presentation, I can only cover a selection of improvements and new features. In many of the more specific talks of my colleagues, you will get more detailed information. This year I will start with some general technology highlights, which are useful for all steps in the design workflow. We have updated our material database to provide more and more accurate material parameters for your simulations. Geodict is shipped with more and better designed GeoApps to solve specific customer requirements. Also, the Geodict GeoApp API was improved. Directly start challenging simulation in the cloud from the Geodict GUI. Geodict has a unified YAML file syntax now to provide easy-to-parse files and a better compatibility with the Python macros and scripts. Allow to render structure outlines in 2D for better contrast, what was used on slide 3 in this presentation. The session macro is available now as dock widget at the right side of the main GUI. A faster and more reliable structure undo redo is available where the old compressed geometries are kept in memory. All Geodict notifications like warnings or error messages, for example during a macro run, are selected at the bottom of the main GUI. Specify which text output, for example from solvers or from Python, is shown in the console window. Furthermore, different output types have different colors now. The settings from GDR result files can be loaded directly in the corresponding dialog. This also works via drag and drop. It is now also possible to manually add graphs into existing plots in a combined GDR result file. At first, we will have a closer look into the very powerful GeoApp concept, where Geodict is used as a platform to develop scientific and engineering applications. This is demonstrated with very useful GeoApps which are shipped with Geodict 2023 to solve specific questions for structure generation, property prediction, and to save images and reports. Some new structure generation GeoApps will be shown in the modeling part of this presentation. In general, the GeoApp programming is very easy using the programming language Python, Python libraries, and the Geodict GeoApp programming API. This allows to create GUIs, define variables, access data in Geodict, for example the loaded geometry, create result files with plots and reports. With the new Geodict version, it is very easy to move challenging simulations into the Geodict cloud, which is run in collaboration with our partner KaleidoSim. If one has a Geodict Cloud user account, one can just click Run in Cloud in most Geodict modules, shown here for Flowdict. Click this button, log in to the cloud account, and the Run command in Geodict Cloud dialog opens. Here one selects, for example, the case name and the cloud machine. Now click Run and the current geometry is uploaded into the cloud and the simulation is started. Additionally, the Geodik Cloud Projects dialog opens, which allows to monitor all Geodik Cloud projects and to download the results. This dialog can be closed and one can continue using the local Geodik installation while multiple cloud simulations are running. To reopen the Cloud Project dialog, go to the macro menu and select Geodik Cloud Projects. Additionally, from the macro execution dialog, one can directly upload complete parameter studies to the Geodik Cloud. For the new Geodict version, we have decided to unify our file formats using the same syntax in all files which contain maps, or in other words, key-value pairs. Such files are, for example, GDR result files and GUT structure files, where the new syntax is shown on the right. Such files can easily be read or written by any YAML parser, and they can be visualized correctly in many editors which support YAML, as shown here for Notepad++. This unified syntax makes it also very easy to transfer data between different file formats in Geodict. A drawback one has to be aware of is that the files in the new syntax cannot be opened by older Geodict versions. On this slide I will highlight some of the main GUI improvements. The first point here is a session macro, which is now available as stock widgets right side of the Geodict GUI. With this session macro section, one can see what was done in the current Geodict session and can record specific steps into a Python macro file. A new part of the main GUI is the notification section, which can be opened via the notification button next to the console button. This section shows the selected Geodict notification messages. If a new message is added, the corresponding button changes its color to inform the user. In the console section, one can now specify in more detail which information is shown. One can select Geodict, debug, Python and solver messages, which are also shown in different text colors now. Now we come to the improvements which are especially important for the geometric material modeling. The restriction to 60 material IDs is gone with the new Geodict version, where up to 265 IDs can be used. It is possible now to automatically create statistical digital twins of foams based on identified pore results from Porodict. Some very useful new structure generation GeoApps are shipped with the new Geodict version. The export of surface meshes for material model geometries was improved, and the remeshing option is available now. The modeling of cylindrical pleat geometries was added. To describe a material model, sometimes 16 material IDs, the limit in older Geodict versions, are not enough. Now this limit is gone and up to 265 material IDs can be used. Here two examples are shown where this improvement is required. The first example is a gray value image of a rock made with a medical CT scanner, where the pore space is, for the most part, unresolved. For this image, we want to define specific properties for single gray values or gray value ranges, resulting in much more than 16 material IDs. The resulting geometry model with 51 material IDs can be seen on the right. This model will be used later when we speak about the Darcy flow solver. The second example is a battery cathode geometry model where we want to specify a volume percentage distribution with 7 different grain sizes or types. With the new Geodict version, one can create up to 8 different grain and fiber types. On this slide, one sees the corresponding input in the gray dialog and the resulting geometry model. If a CT scan of a foam is available, this image data can be used now to automatically create a statistical digital twin for digital material design. As a first step, the foam is imported and segmented with Geodict. Now one runs identify pores from Porodict and loads the GDR result file into the random foam generator dialog. This process is shown at the bottom of the slide, where the segmented CT scan is shown on the left. In the middle, one sees the visualization of the identified pores. Loading the corresponding GDR result file into PhoneGeo, one can automatically create the digital twin shown on the right, which has the same poor characteristics as the original CT scan. Geodict is shipped with many interesting structure generation GeoApps. A few of these GeoApps are presented here. New in Geodict is a GeoApp to automatically create a digital twin of a granular geometry based on an image of a real material. This GeoApp computes properties like the solid size and the pore size distribution of the real image and the geometry model and minimizes the error between the two using an optimizer from SciPy. On the top right, one sees the original image and the digital twin of a carbonate rock microstructure. Also new in Geodict are two GeoApps to create bimodal anode and cathode geometries of lithium-ion batteries. On the image at the bottom right, such anode and cathode geometries are combined into a battery geometry, which can be used in BatteryDict for charging simulation. Another example focusing on fibrous laminate composite geometries is the GeoApp LamiGeo, where a resulting geometry is shown now at the bottom right side. This demonstrates how the GeoApp concept can be used to easily automate and customize the Geodict structure generation. With Geodict, one can create great geometry models of many different materials. Sometimes one might want to do a specific simulation on such a geometry model outside of Geodict, for example with COMSOL or ANSYS. One way to do this is the export of a high-quality surface mesh of the geometry model. This workflow is shown here for cathode geometry. At first, one creates a multi-material partition of Unity surface mesh with MeshGeo. Now one can use the remeshing option to reduce the number of triangles, providing a good quality surface mesh. Here the mesh was additionally smoothed to get even rounder grain surfaces. The resulting mesh with 500,000 triangles was exported and afterwards loaded in COMSOL, what is shown on the right-hand side. Now the Geodict geometry model can be used for simulations in COMSOL. Now we come to the highlights regarding the image processing and analysis. With the new Geodict version, one can import and handle multiple gray value images at the same time. For the AI segmentation, one can also choose a random forest method, and one can select the used image features for boosted tree and random forest. It is possible now to train neural nets as gray value image filters. To correct rotations between single images in a 2D image stack, for example from FibSim, image alignment based on the SIFT feature detection is possible now. With the new Geodict version, CT scans in the DICOM format can be imported. A specific neural net to identify binder and graphite anodes was added to identify binder in GrainFind. As first point in this section, I will show the improvements in the AI image segmentation. As AI model, one has the additional choice random forest. Other choices here are boosted tree, unit 2D and unit 3D. For boosted tree and random forest, one can select the used image features now. The new mixed overlay mode makes it much easier to label critical image sections, as one can see the preview and the labels at the same time. Furthermore, the runtime and the memory requirement of the AI segmentation was reduced drastically. On this slide, the unit 2D AI segmentation is shown using a cathode FibSim image. This image is part of some example 3D images which are shipped with the new Geodict version. It is now also possible to use Geodict AI with gray value input and gray value output. In this way, one can train specific image filters which can be used in image processing. On this slide, some project results together with the KAUST University are shown. The aim is to improve the image quality of a fast, low-quality scan using AI, where the training data is high-quality scans of the same regions in the sample. The resulting AI-filtered low-quality image is shown on the right. It has better contrast than the low-quality image and the conventionally filtered low-quality image. It also has less noise than the high-quality image, which was used for the training. Overall, a very nice result, which highlights the potential of AI image filters in image processing. The last part of my presentation will focus on the highlights regarding property computation. With the new Geodict version, one can consider concentration-dependent electrolyte properties for battery charging simulations, perform very fast charging simulations on the mesoscale using the best mesosolver which is now available in Geodict, compute battery degradation via volumetric changes during charging simulations. The Lear solver is now also available for effective stiffness mechanics simulations. It is now much easier to set up two-phase flow simulations with mixed wet conditions. A direct Darcy flow solver is available now in FlowDict. With a new version, one can compute molecular diffusion in the intermediate or slip regime. One can easily compute flow and filtration in complete filter geometries. It is now also possible to compute coalescence filtration in FilterDict. To perform very accurate battery charging simulation on large microstructures can be time and memory consuming, even with the fast battery dict solvers. For the example battery on this slide, created with the bimodal anode and cathode GeoApps, the best microsolvers did run for over 60 hours on a fast 16-core machine in Geodict 2022. Using the new version of the best microsolver, the runtime is reduced by more than a factor of 5, and the same simulation takes only over 11 hours, which is in this case even faster than the Lear solver, but takes considerably more memory. With the new Geodict version, it is also possible to perform an even faster mesoscale simulation on this accurate microstructure model, choosing the solver best meso. All the parameters needed for this upscaled simulation are computed automatically on the microscale and passed on to the mesosolver. In this way, the simulation time goes down to 11 minutes and only 2 GB of memory are used. The mesoscale simulation predicts the charging or discharging behavior of a battery or half cell, but it does not provide detailed results on the microscale like the voxel-wise lithium concentration. The charging curve results of the micro and the mesosolvers are compared in the plot on the right. Up to charging rates of about 50%, results are very similar. For large states of charge values, the results deviate, probably because here the detailed microstructure plays a more important role for the charging behavior. A very interesting question for battery developers is what strain and stress values appear in a battery during charging or discharging due to changing lithium concentration in the active materials. This is one of the most important reasons for degradation in batteries. With the new Geodict version, the degradation via volumetric changes during charging simulations can be computed directly in BatteryDict. One needs to specify the mechanical properties of all constituent materials and the material expansion due to changing lithium concentration in the materials. The results, shown here for the charging simulation from the previous slide, are the information of strain and stress per voxel for a given state of charge. This is shown on the right for strain in the binder and stress in the anode active material graphite for 70% state of charge. It is also possible to compute, for example, the layer-wise maximal von Mises stress in graphite, as shown in the plot at the bottom of the slide. As next point, I want to mention that our fast and memory-efficient solver Lear is now also available in ElastoDict to compute effective stiffness and thermal expansion for linear constituent materials. This new solver is very effective and memory efficient for linear simulations with highly porous materials, especially with symmetric boundary conditions. For all other simulations, the fast and reliable Fielmann solver is the best choice. This solver allows to do large deformation simulations with non-linear constituent materials, modeling, for example, plasticity, damage, and failure. Previously, the SATODict user interface was designed for cases where all contact angles are below or above 90 degrees. In these cases, the wording wetting fluid and non-wetting fluid made sense, but it becomes confusing for mixed wet cases where contact angles below and above 90 degrees are present. In the new Geodict version, the user interface was reorganized and is now suited for mixed wet conditions. Post-imbibition simulations can directly be set up in the GUI and do not require a GeoApp anymore. Other improvements are the new parallelization options, which allow to choose the number of cores used for parallelization. A new stopping criterion was introduced to stop simulations based on a given saturation of the invading fluid. The output options are reorganized and extended to reduce hard disk space usage. The new Equation and References tab completes the simulation dialog and support users with detailed information about the used methods. An example of a two-phase fluid flow with mixed wet conditions is shown on the right side. A three-layer GDL is shown with hydrophobic at top and bottom and hydrophilic in the center. Water invades from bottom to top. Observe how the water wets the hydrophilic part almost completely when a water droplet touches it from the hydrophobic part. It is now possible to perform Darcy flow simulations in FlowDict. Permeability computations are very challenging on segmented rock structures which were acquired by medical CT scanners. Usually the pores are not resolved besides single big cracks and thus no percolation paths through the structure exist. With our Stokes-Brinkmann solvers, it would be possible to consider a permeability value for each segmented gray value region, but unfortunately the runtime of such a simulation is relatively long. The new Darcy solver can deal much better with such simulations. Here the Darcy instead of the Stokes-Brinkmann equations are solved, whereas the viscous term is neglected. Support of 265 material IDs in Geodict allows to solve Darcy almost directly on a gray value image when a gray value to permeability map is available. An example is shown in the right-hand side. A large medical CT scan from Petrobras available at Digital Rock Portal was used with a gray value to permeability map as shown on the top right side. The gray values and the velocity fields of the simulation are shown. Here we compared Lear Stokes-Brinkmann and Lear Darcy. The computed permeability is almost the same, but the Lear Darcy is almost 70 times faster. In addition, Lear Darcy requires only 25% of the memory compared to Lear Stokes-Brinkmann. Diffusion in complex microstructures is governed by two processes: particle-particle collisions and particle-wall collisions. In cases where the mean free path of the particles is in the range of the characteristic length scale of the microstructure, one is in an intermediate regime. In this regime, where the Knudsen number is in the range of 1, both processes must be considered, what is done in Diffudict molecular diffusion. This is shown here for a geometry model of a microporous layer from a gas fuel cell, where the gas has a mean free path of 68 nanometers and the geometry a characteristic length scale of 27 nanometers, resulting in a Knudsen number of 2.53. If one solves the Laplace equation or considers only the particle-wall collisions, the computed effective diffusivity is overestimated by more than a factor of 2 compared to the correct molecular diffusion result. The computed effective diffusivity values are shown at the bottom right of the slide. So with Diffudict, all diffusion regimes are handled correctly. With the new Geodict version, we have focused on making flow and filtration simulations for complete filters much easier to use. To import a cut geometry of a filter's STL or OBJ file, to set the correct materials and to define inflow and outflow regions should be straightforward now. After the geometry pre-processing, just use the new dialogues in FlowDict and FilterDict to set up your flow and filtration simulations. The resulting local pressure drop of a complete filter flow simulation is shown on the right side. An additional feature in the new Geodict version is the design of cylindrical pleats, shown in the video on the left side. So one can import a filter housing and design an optimal pleat structure for a given filtration application using Geodict. Finally, I want to mention the coalescence filtration. Many filtration applications focus on removal of liquid droplets, for example the filtration of water or oil aerosols from a gas. With the new Geodict version, such filtration processes can finally be simulated with FilterDict. On the left one sees the results of a realistic coalescence filtration, and on the right the growing of a liquid droplet on a single fiber surface for different contact angles. I hope you enjoyed my presentation about some of the highlights in our new Geodict release. Hopefully you heard about something you want to try or you have learned something new. If you have additional questions, just contact us and we will happily provide additional information. As mentioned in the beginning of my talk, many of the highlights shown here will be discussed in more detail in the talks of my colleagues. Thank you for your attention.